All right. Hi guys. Um okay, back again. So yeah, last week okay, I'm just going to talk about last well, last week and my ideas for this week for the problem we have. And yeah, that's that. And then we're going to try to solve it. And you can also drop your ideas as well. Okay, so last week we tried to build a basic autocorrect system and it was quite fun actually. For me personally, I learned quite a good deal. Um, the biggest takeaway for me was seeing how I could solve problems, or validating again that I could solve problems that involved probably algorithms and data structures without having to know the intricate details of these upfront, but being able to learn, knowing the basics and being able to learn the rest as I go on. And then there was also the issue of domain knowledge. To solve a problem in a particular domain, you need domain knowledge. Like we were trying to solve problems in the autocorrect space, so we needed to understand some linguistics and all of that. And for me personally, because I already understood it to some degree, it was not much of a reach for me. So I didn't have to do so much reading up because I knew a lot of I'd already been familiar with it to a degree. But yeah, if you can understand the problem domain and translate it into the code you know or how you think to solve problems, then you're not that far away from the solution. So okay, that said, let's move on. Let's see. So today we want to try to build something that can detect colors in an image, not just colors but major colors in an image. So for instance, my wallpaper here, I don't know what I actually don't know what the results will be like, but I'm guessing to be something with the purplish hue as like the major color. I don't know if you guys if you've noticed it, but Twitter has this feature where you can customize the color of your profile and all that. And I'm trying to recall which site I'm thinking of. I don't remember which, but there's a site I I use that has when you set the profile picture, it automatically matches the rest of your profile, the rest of your experience on that website. It matches it the to the major color it detects in your profile picture. So it's a really neat thing. So for instance, for this picture, it would probably the rest of your profile will probably be have like shades of purple all over, something like that. Um, for a picture like this, it probably have some bluish color and all that. So yeah, I want to try to do something like that today. And okay, let's go. So uh, yeah, so the first thing, okay, my reasoning how I approached this today. Um, okay, compared to last time, I don't have as much domain knowledge as I did then. I don't know so much about images and colors and photos and files. Okay, I do know to a degree, but when it comes to manipulating the code, I don't know much about it. Generally, I even stay away from manipulating files with code. I have an irrational fear of that. Anything that has to do with the file. So, but yeah, I had to go in and first find out what this is about. Okay, I know that images. I know that you have images. Computers read them as some form of binary data, but that was pretty much that was what I knew, but I couldn't find concrete answers. So I went to look on the internet as usual, and I came across some nice resources. Initially, actually, I was just looking straight for an answer, something like why how to detect colors in an image or in a pixel, something like that, because I knew it was going to be per pixel. But then I realized I needed to back up because the answers I was finding were quite confusing. In fact, were not helpful at all. So I backed up a bit and went to look at some other sites. And I came across this nice article which was actually really what I needed to know. Introduction to Digital Images. I think it's from a course here at Stanford. So yeah, just explaining how the whole digital images thing works. A digital image is an image. Let's just say an image on your computer, because it's digital. You can't touch it. So it's a digital. It's stored digitally. It can also be analog if your computer is an analog machine. But yeah, it's stored digitally. So yeah. Just my takeaways from this. I'll share the link, so anyone that wants to can also take a look at it. But for me, my takeaways from this, first off, digital images are computers read them as a series of as binary data basically. So you could think of it as a series of numbers. Yeah, a bunch of numbers that describes what the image exactly is, and yeah, like I said, yeah, behind the scenes, lots of little numbers. So it's a bunch of numbers to the computer, which makes sense, and put together, rendered by a, the right program. It forms an image, that a beautiful image that we can see like this. So pixels, for those that aren't very familiar with them, the pixel is like a square, a tiny square on each in a picture that makes up a component of the square of the picture. So each picture is made up of multiple pixels, and each pixel has only one color. So I don't think this is the only way you can represent an image digitally, but I think it's the most prominent way, or the most colorful way. Sorry, most effective way, because it makes things easier for the computer. Just create a bunch of pixels, give each pixel a single color, and you can form your image. I mean, theoretically, you could probably find a way of giving a pixel multiple colors, but I don't know how that works. You need to do pieces like specify, okay, this section has this color, this section has this other color, but it might not be very efficient from a software point of view, or software and hardware actually rendering and processing. So and pixels don't have like a fixed size. They are the size of the pixel could vary. So if an image, generally for smooth digital images, you won't see pictures. You won't see the pixels. Like if you look at this image here, you can see that you can see the pictures, the pixels in details, these tiny squares. Okay, sorry, I don't know how good the resolution of this video is going to be back there, but if you go to this page, you see that the squares that make up this picture are visible, and those are the pixels. But for higher resolution, you would probably use pixels that are smaller pixels, so you have more pixels and create a higher definition image, like probably like what you see on my desktop. You can't see the pixels because it's higher definition, more pixels, smaller pixel sizes. So two photos can have the same amount of pixels and actually look differently. So that pixelation effect, when you see an image that is pixelated, it's it all comes from increasing the size of the pixels or using larger pixels, uh, and then since each pixel has a single color, the image then starts to look more blurred. So yeah, so to get the number of pixels in an image, usually when you see an image dimension, like you see 800 by 600 or 1280 by 768. That means you have 1280 pixels wide and 768 pixels vertically. So you multiply and get the number of pixels in an image. Yeah, megapixel is 1 million pixels. Then to locate pixels, there's an XY grid of pixels. So you start here at the top left. This is like the 0, 0, the origin, and then going to the right, you're increasing your x coordinates, and going down, you're increasing your y coordinates. So to locate any pixel, you just need the coordinates. So each pixel, like we said, each pixel has a single color, and the colors are represented in usually RGB format. Okay, before we get to RGB, let's talk about grayscale pictures. Grayscale pictures like black and white pictures. Here's another useful article I found. Yeah, let's a picture like this. A picture like this. Okay, black and white is not exactly accurate because it isn't black and white. It's grayscale. It's made up of different shades of gray. So yeah, grayscale pictures. And for grayscale pictures, each pixel has a single value, and that value is like the intensity of gray on that picture. So this pixel will have, okay, I think I even have a tool that should be helpful here. This is a color picker tool. I don't know how much help is going to be here. But each pixel is going to have a value of gray. The value you see, like if I click here, this value is the hex value of the color that this pixel has, and it's a shade of gray. So each single pixel in this has a shade of gray. And so that means theoretically, if you wanted to represent this as a computer, you could probably just, if you had a series of, if you knew what the gray values were, you could just like write down the values of gray for each pixel. So you have 200, 200, 200. Like the first three pixels all have the same gray intensity. Then maybe it goes down a bit, 194, 194, and then 200 and so on. And then you could represent it in a grid. You would have something like this, maybe. And yeah, and so on and so forth. You could like from the grid. So the grid will correspond to the actual picture we have here, like the square grid or the rectangular grid like you have over there. And yes, okay, something else I forgot to mention is that these pixels here, the intensity, the value of the pixel is usually a number between 0 and 255. Now, I'm sure we've probably come across this kind of range before, especially people that work with CSS. But I don't know if everyone knows why we make use of those values. And the reason behind the whole 0 and 255 thing comes from number of bits in a byte. So at the very minimum, I think you could store each pixel as a single byte. Like you know bytes are how the computer stores data. So, and a single byte is 8 bits. So if you're storing, if you store every pixel, I didn't. If you store every pixel as a single byte, yeah, so that means you have 8 bits of color for each pixel. I think theoretically you could actually store less than 8 bits, like less than a full byte for a pixel. I mean, if you don't need all of that, but let's just say for a standard definition, you'd store a pixel as 1 byte or 8 bits. Now 8 bits means that you have 1, 2, 3, 4, 5, 6, 7, 8. Eight different positions or 8 different digits, possible digits you can have there. And for this, that means you could have, remember binary zeros and ones, so that means you could have, with this set of 8 digits, you could have lots of different numbers. So 0, 0, 0, 0, 1, 2, 4, 5, 6, 7, 8. You could have that. You could also have this, and so on. I think we get the idea. So this is 1 in binary, this is 2, and this is 3. So yeah, so how do we know the total number of possible values we could have for a single byte? That's the number of possible combinations of zeros and ones we could have inside of a single byte. It's actually a quite straightforward calculation, 2 raised to the power 8, which gives you 256. If for those who aren't familiar with why it's 2 raised to the power 8, it's because of you could say permutations and combinations. Remember when you learned that in maths and maybe didn't pay attention? But yeah, if you have 8 possible slots, if you think about it in a moment, you realize that this is correct. If you have 8 possible slots for doing something, and 2 possible ways of filling each slot, like 1 and 0, 1 and 0, 1 and 0 for each slot. So the total number of ways you can fill, the total number of combinations you can have is 2 times 2 times 2. That's 2 for each of the 8 places. And that gives you 2 raised to the power 8. So that's how you get your 2 raised to the power 8 value. 256 possible values of a single byte. So that means there are 256 possible values of a single pixel, and that's why you have 0 to 255. Do that because it's 256 different numbers. So yeah, 0 means nothing, 255 means like full saturation. So that is what happens when you store a pixel as a single byte. And for grayscale pictures, I mean, that's probably straightforward. Just make a pixel a single byte, and you just have the value of the byte is the intensity of the gray or the shade of the gray if you want. But for color pictures, like let's say something like this, okay, this is an example of the picture grid. And yeah, while it's actually a grid, you could send it again. Okay, let me share this link as well for anyone that needs it. It's a grid, but you could also send it. I think computers actually read it as something called a bit stream. That's like a series of a series of numbers. Well, we'll get to that in a bit. Anyway, yeah. So over to colored pictures. So, when it comes to colored pictures, the concept is quite similar, but in this case, we've moved beyond having 1 byte, and now because we have 3 different possible colors: red, green, and blue. And again, it doesn't have to be those 3, but that's a system of representing colors. One of the systems that people have come up with: red, green, and blue. It represented color as a value for red, green, and blue. Um, so we could. I wish there was an easy way to clear this board, but no. Let me just get the eraser. So we, instead of representing, no, why do I need to clear this now? Instead of representing a single pixel as 1 byte, you can represent the pixel as, say, 3 bytes. So for each color you have 3 bytes. So you have in fact, since I have a list of 3 bytes here, I'm just going to make use of this at once. So you have 1 pixel represented as 3 bytes. So that gives you something like this, and those 3 bytes are RGB colors. So you could say that this is the R, and this is the R, this is the G value, this is the B value. So each value of the color is between 0 and 255. So to get the color that the pixel holds, it's all value. It's a value of RGB for each one. So that means a pixel's value could be something like 0, 255, 140. So that means you have a pixel that has a color that is mostly green with some blue. I don't know what that would look like, but yeah. So that's the whole basic theory behind it. So with that, I'm thinking, so we want to get the prominent or the dominant color in an image. So my basic or my naive theory for that, I don't know actually how correct it is, but I think we could do a simple calculation where we get the color in each pixel. So that's an RGB value, and then we find the average. We just find the average color essentially. So we sum all the RGB values from all the pixels and divide by the number of pixels, because it is, after all, it is just a series of numbers. And yeah, so I think that could work. So find average of RGB values. So yeah, I think that could work. But a bit more fun with pictures before we go into looking at this. And if you have any ideas, or if you think I'm of any better ways of doing this, any suggestions, anything, feel free to drop in the comments. But before going ahead with this, in the meantime, I also wanted to have some fun with pictures. Like I wanted to see this actual thing in front of me. And so, okay, one more thing. When you think about this, so with this kind of, we remember that with the original system where you just have a single byte for color, it could be, you can only represent maximum of 256 values, and it doesn't have to be grayscale. Actually, it could be your regular color system, but only 256 possible colors. So actually, arbitrarily, you could say that 0 means red, 1 means blue, 2 means purple, 3 means yellow, things like that. You could actually just arbitrarily decide that, and then down to 255, for a single byte system, on the 8-bit system, you could actually just decide that, and then whatever software is rendering it reads the pixels and renders that color based on that. But you can see how very limited it is. We can only represent 255 possible colors here, so that's why it's better to just use this 1 byte system for only grayscale, and use a better 3 byte system for colors. And the reason is that with a 3 byte system, if you have 256 possible values for each channel, that's what they're called actually, red, green, and blue. That means you have a total of remember that you have 8 bits, 1 byte for each one, so 8 bits, 8 bits, 8 bits. So that gives us 8 times 3 bits. That's 24 bits, and that means the number of possible colors we can have is 2 raised to the power 24 bits. And if we do that, if we run that calculation quickly, I don't know where exponential is. Okay, 2 raised to the power 24. No. Is that's not exponential. That is, oh my god, I'm really not familiar with my calculator. 2 raised to the power 24. Yeah, that gives you 16 million. And this is where, I don't know if you might have noticed, maybe you bought a TV or some other display device, a laptop or something, and they usually write like 16 million colors. They could write something like that available. So this is where it comes from. Representing a pixel with 24 bits of color gives you the ability to move, like, it's a drastic change actually, from 256 possible colors to 16 million colors. I mean, that's quite impressive actually. So yeah, I mean, I actually came across this some time ago too, when I was just trying to do some research into 8-bit colors. I mean, I you know how people talk about 8-bit games, all those games we used to play back then in the 80s, 90s. I mean, I wasn't born in the 80s, so nah, but in the 90s, those are the games then. I probably didn't play them until like 2010. But yeah, those games that looked very basic. They were called 8-bits. Well, the 8-bit name there is not actually technically, it's not so much a technical description as more of just a colloquial name. But part of it is, this is the extension of part of it. They were also limited in the number of colors they could represent at the time. So yeah, that's some interesting knowledge about colors and pixels. And then I tried to look at, so supposing an image, so assuming an image like this actually has a number of pixels horizontally and a number of pixels vertically. So I was thinking, what if I could open this image and actually look at the pixels? Because if you have the actual pixel data or the bit stream like this, and you modify the pixels individually, that means you could actually change this image. And probably that is what image modification software does. They change the pixels, they modify the pixels, the actual pixels in the image. So, but then another thing to note is that you need to do this with an actual raw image. I'll explain in a bit. So I tried to get this image. Okay, let's do that. So I downloaded this image. And I think, okay, I downloaded this image, and yeah, here it is. So I actually want to explore the pixel data inside of it. Let me see how many pixels there should be in here. So this is 808 by 538. So let's see how many pixels should be there. Where is my calculator? I've closed that shit. 808 by 538. So 8 by 538. So that's 404,000 pixels should be in this photo. But so if we're representing a pixel as a single byte, that means we're expecting that it should have a size of 404,000 bytes. So that's like what, 434 kilobytes or something. But if you look at the actual image, the size is like 229 kilobytes. Why is that? And if we are representing it as 3 bytes per pixel, it would be much more. It would probably be like it would be 1 million bytes, so that would be like 1.3 megabytes. But you can see that the size is actually less, much less than that. So I believe this is because of compression. Most images, if you're storing an image in raw format like that, where you have a number of pixels, you have 3 bytes for each pixel, three bytes for each pixel, or 24 bits or whatever, and you decide to store it like that. I mean, you can imagine we would have lots of very heavy pictures. In this particular case, this picture will be like 1.3 megabytes at least. So just to view 5 pictures, you've already spent 5 MB. So most image formats are compressed formats. Like you have JPGs and PNGs, even GIFs. Like this is a GIF file, or GIF as the series call it, right? Even GIFs. This is a GIF file. They have some form of compression, some lossy, some lossless. But yeah, the data is compressed so that you can have like more efficient photo storage and rendering. So because of that, we don't get the full 498 something kilobytes. We get like just 200 kilobytes, which is almost half of that. And the way the compression works, or like one way compression could work is by looking at surrounding pixels. So rather than the computer storing this pixel has this color, this pixel has this color, this pixel has this color, if all the pixels have the same color, we could actually, if all pixels from here to here have the same color, we could probably just write, okay, 9 to 25, that like the pixel number has the same color. So like in this example here, since these first 3 pixels have the same color, we could probably just write something like, assuming our grid was okay, x and y. So x comes first, y comes second. So 1 1 2 3 1 all have the same color, 200. So like that, with instead of using 3 bytes for each other, and then we could then represent them in a single byte possibly, or maybe 2 bytes or less, maybe 1.5 bytes or something. But yeah, we wouldn't need 3 bytes for this again. So imagine the color was 255, and we needed to represent a sequence of pixels. So we could have a single byte. This is the byte that holds the color. Okay, the color can be 255 because it's three color channels. But I'm not sure exactly, but there's it's all of you compress the color values into one. Okay, or you could even have those 3 bytes. 1 2 3 4 5 6 7 8, and let's see. So these are the 3 bytes for the color, and then you could have an extra byte that states the pixels that have the same color. So let's say it's pixel 0 to pixel 50, or pixel 0 to pixel 2. So in binary that would be 0 0 0 0, that's 2, that's 0, sorry, and 2. Let me move this. So these last two represent the bytes, starts at this byte, stops at this byte. I don't know, you probably present it in some format that makes it obvious, and probably you could combine these two actually into the same value depending. But yeah, so rather than having these 3 colors repeated, in this case 3 times, because it's 3 pixels, 0 1 and 2, you will just have these 3 written once, and then you specify which bytes or which pixels have it. So yeah, that's how compression could work. So because of that, it's not straightforward to see the raw pixels. I tried to get the raw image. That hadn't been compressed, probably from a camera, directly from a camera or something. I was able to get this, but okay, yeah. So let's try to calculate how many pixels we're expecting from this one. This one is raw. It's an NEF file, which I guess is how Nikon cameras, or is it pronounced Nikon? And it's how they store their raw files, because apparently raw file formats vary by manufacturer. And okay, so let's do a quick calculation to see how many pixels we expect here. That's 4016 by 6016. And you can, sorry, just to note, you can see that this is larger, the second dimension is larger because the height is larger. So 4016 by 6016. So that's 24 million bytes. So we're expecting at least 24 megabytes. And you can see in this case that the size is actually more than this. The size is actually more than the expected size. It's 30 megabytes. And that's probably because raw image files from the camera, before they are processed and compressed to like JPG or PNG, usually contain other information about the picture. Like you can see this contains information about the camera, and then the device name and the conditions when it was taken, and then the date and time could also possibly be there. Oh right, the date is even here, 21st January 2018 time. And then you could also have I think also sensor information is usually there too. That's information about different sensors. I don't know. So because of that, again, we can't just have a dump of the raw data. I don't know if anyone knows any ways of doing that, but I couldn't find any ways of getting that. So okay, getting back on track. So briefly, so I just decided to take a look anyway to make a run for it and try to look at the pixels data. So apparently you need a kind of software called a hex editor, or that's one software you can use. You can upload an image and it gives you the hex data, which is the actual, I think you could say pixels. No, okay, not necessarily actual pixels, but the bit stream, which is like the series of bits that the computer reads. Let me try with this one and see what goes on. Let me try with one of my images. Yeah, so this is the bit stream. And even though it isn't exactly, remember we're expecting 400 something thousand pixels for this, and it turned out to be like 200,000 because it's compressed. And yeah, I can see this is the current address, this is the last address in hexadecimal. And so these are like all the different values. But I think if we modify individual values here, we can still change this image to a degree, and we're gonna try that. So let's try that just for fun and see what happens. What happens if I delete this? No, okay. Let me be sure. So let me try to delete a couple of bytes. So how many bytes should this be? 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. Interesting. I'm not really sure about the details of this whole bitstream and hex editors, but I think I'll probably go and read up like on it more afterwards. But yeah, deleting this. So that's 208 bytes, and 208 bytes divided by 12. Because I want to know. What? Okay, I was not expecting that result, but we move. So 28 bytes. Okay, I don't know how that number came around, but here we go. So let's delete it. And the image might be corrupted. I don't know, because it's possible we deleted the bytes that hold information about the encoding or something. I don't know. So without those bytes, pictures, software might not be able to read it. But anyway, let's try to take a look at what happens to the image. I think there's a way you can export. We can open this file. So we've corrupted the image. So let me try again. Let's try removing a different set of bytes. No, I don't want to select anything. How do I remove selection? Okay. Yeah. Okay, so let me try to remove some bytes from somewhere in the middle. I don't know. Hopefully, we don't delete any bytes that prevent the image from loading. Well, I think we probably will, sure. So export this, save, open. Ooh, baby. So this is what we get. So just those. We just did that 144 bytes, and we've lost most of the image. Interesting. Let's try again. Let's try deleting different selection. So let's just try removing a few bytes here. That's 2 bytes. 16, 16. Okay. Let's export this. Still no difference, or still similar thing. So it's possible that getting rid of those bytes probably messes up most of the image, like messes up another part of the image that makes everything just render as black. So yeah, okay, I think we've had quite a lot of fun now, and we can go ahead to try to write this. Okay, one last time. Okay, nice. So okay, so over to now. How do we do this? Remember, back to our main aim. I think I can close this for now. Oh, this is okay. This is just another interesting site. I'll drop this link to you in case anyone wants to take a look at it. But this was about converting bit streams to actual photos, and yeah, this is the bit stream just like you saw in the hex editor. And for anyone who likes knowledge, can have this. Okay, I'm not using this anymore. So interesting. Why do math? I like the name. I like that website. So yeah, I was looking for how to do this in Node.js and image manipulation library, where we can get not necessarily manipulation, but like look at an image and get the value of a pixel at any point. And I came across this. But before we go to that, just wanted to mention, I probably have mentioned this before, but that this picture you see here, these 3 versions of this picture are like when you turn off other channels. So like, god damn, why am I saying like so many times? Remember each pixel 3 bytes of information, RGB. So you can have, if you decide you only want, maybe if your software only reads like, if you tell your software to only read the values, or if you store only the red values, this is what you get. Same if you store green, and same if you store blue. So the parts that are really dark are the parts that have the least amount of red. And then a similar thing for other pictures. There isn't much blue in the picture overall, so the blue generally is quite dark. So yeah, I think you could do this in most images. And like I said, RGB isn't really the only way to store process colors. Front-end devs would know probably. Okay, there's hexadecimal where you have a hex value, like, and I think the library we're working with will return the pixel color in that format. So instead of having RGB or 3 bytes 1 to 3, you would have a value like, you would have the hex value. So 1, 2, and 3. So hex, that's base 16. Also, I mean, there could also be transparency. But I don't know how much that applies in our current scenario. But yeah, RGB. So that's the hexadecimal we could do. And okay, no. Okay, I just said a bunch of rubbish because this is still RGB. This is just like a different representation of RGB. This is hex format, this is like in decimal format, and then this is probably in binary format, but it's still RGB. What I meant to talk about was different color spaces, as like a whole different theory of creating colors of combining colors, not using RGB but rather using something different. So I think I don't know much about that, but okay, I think there's this one where you have luminance, yeah, YCBCR. So Y stands for luminance, and CB and CR stand for chrominance. Yeah, okay, but I'm getting carried away. And there's another one I've seen around, HSL. I'm not sure exactly what that stands for because I've never bothered to know. But yeah, different ways you can represent colors, and computers probably use some of this. And this is what happens with the YCL, YCRCB version. With this version, I think there are channels of, yeah, this is what you get on the Y channel, CR, CB, and combining them, you actually get this. Quite interesting. So that was just some fun with colors for anyone that wanted to know. So let's go over to actual processing of the image. Now, what I'm thinking is, remember what we said we'll do. We'll get color in each pixel and then find the average, which actually is a quite simple algorithm at the end of the day. I don't know if this is the best approach, or if this is, or if this will even give us the correct result actually, because finding the color in each pixel means we're going to have to iterate over every single pixel. And remember that the number of pixels you could have. Remember for this image, or for the other image, we had like 400 and something, 400 something thousand pixels. So that's 400 some thousand iterations. But I don't know how efficient that would be. But let's give it a try and see. So yeah, GIMP, JavaScript Image Manipulation Program. Okay, so we're going to try to get pictures from, or colors from, some images we have, and just going to copy this code for a starting point. Okay, so this is a node file, and I don't need this. Okay, so we're going to run this as a command line program. So we'll pass in the argument to it. Okay, so we're going to get the file name as an argument, as a CLI argument, and that should be, I think, 1. argv0 should be the name of the script, and then I think argv1 should be the file name. Either way, we'll find out. And okay, so how do we get pixel values there? Yeah, so here you can get pixel color at an XY coordinate. So let's give this a try and see what turns out. And then this will return the color in hex format, and then you can convert the hex to int RGB. We'll need to convert it to int so that we can take the average, because I mean, you could find the average in hexadecimal because it is a number after all in a different base, but so that we don't run mad, I think it's just easier to work with it in decimal. I don't know. So yeah, so photo, this is our photo. Okay, we're going to do something here. So what I want us to do is we're going to get, I'd like to see what this does. Oh, right, I need to npm I GIMP, and yeah, so we'll get the pixel colors. But what I'm thinking of us doing is writing, when we get a pixel color, we're then going to write that as a new image so we can see what it looks like. Okay, so I want to see if we can create an image and like populate it with this color. Right, sorry, my bad. This should be color, these American spellings, and then we'll decide what to do with this color. I want us to like have it output in a format that helps us easily see the color that we've gotten. So first off, I'm gonna console.log, and we haven't defined our x, so I will come to that in a bit. But we want to console.log. Again, we'll convert it to an int, so it's easy to see. Int to RGBA. Color. What is going on here? Why is this? Oh, okay, still updated. Okay, so yeah, let's just start with this. We'll get a random pixel and console.log that. Am I done? Yeah, let's just start with this. Get a random pixel. Let's say 500, 300. I'm okay. I think there should be, because the image you're dealing with had, I think. Okay, let me open the image up again. Yeah, it's, you know, he had 800 by 500 pixels, so yeah, that should work for us. Should be good. Okay, so then we run this node. Is it argv1 or argv2? I'm not sure. Okay, here we go. Okay, no, it should be argv2, because I think the first argument on the command line is the full path to node. The second argument becomes the script, name of the script, the full path to the script, I think. No, the name of the script. And then the third argument is, the rest of the arguments are what you passed in. So I'm going to pass in this file. Let me get the file path. Okay. Okay, folder path. And then the file name. I don't know why Windows keeps hiding file extension. Oh shit, I didn't copy that. Oh god damn it. Why the fuck? Was this the node copy? Copy. Okay. .gif. Let's see if this works. Oh, interesting. So yeah, it did work. This is the color of the pixel at 500, 300. This is, let's also log it in hex. I'm going to try to visualize this color and see what it's like. Okay. So yeah, run this. So this is the hexadecimal color. Is this hex? Is this hex? Okay. Why does it have so many values? Isn't the hex supposed to be like 6 or 8 values? Oh, okay. And then this is the RGBA. I'm a bit stumped here, because I think the hex is supposed to be the hex value should be 6 RGB, R2 for R, 2 for G, 2 for B, or 8, let me like 2 for the alpha, which is transparency. Well, let's go back and look at the docs and see what they had to say. Your XFF. So maybe convert it to, okay, maybe convert it to like base 10. Okay, yeah, int to RGB. It is an integer actually, and in base 10. So if we want the actual hex value, how do we get the hex value? Okay, we could just convert this to base 16 then. because hexadecimal is base 16. And how to convert? Is there? I think there should be an easy way to convert to base 16. Please tell me there is a straightforward way. An inbuilt function, please. Okay, cool. To string. Nice. Yeah, I actually forget. I forget quite often that you can convert that to string. Actually takes a base or radix as its parameter to convert to that number. So that's quite simple. So yeah, this is the value in hexadecimal. And how do we visualize this color? There are a number of ways. I think a quick way I can do is just let's see, create a CSS file, because my IDE like highlights colors in CSS files. So I can just create a CSS file, write some bogus selector, or write some, yeah, so this is the color that was picked for that pixel. This color that was picked for that pixel, 500, 300, and roughly, wait, let's see where that position is roughly. 808 by 538. So 500, 300 should be 500 should be somewhere around maybe here, and 300 should be somewhere around here, I guess. So yeah, somewhere in this area. So yeah, that makes sense. Let's try to get the color of the pixels as so 808 by 538, and okay, we're gonna do it again, and screw you and your const. Let's get the color of the picture at the corners. I don't know, I think that white border is part of the image, the white border here, so that means both of these answers should be white. Yeah, white. F. So yeah, both of them are white. Let's move inward. I want to see. I want us to get some colors maybe of the screen here. So this should be like maybe 500, and let's say maybe 50. I don't know. 50 is probably too small. I mean, if this is 800 pixels. Maybe 50 pixels will still be white. So let's just say 200 pixels. 200 by 500. Then I need this. So yeah, this is the color. Copy that. And yeah, it's a shade of green, I think, which is what we're expecting down here. So yeah, okay, I'm starting to get hungry, so let's move on and write the algorithm, or convert the algorithm to code rather. So what we need to do now for each pixel. Okay, one last thing, I want to see what happens if we try to access color of a pixel that probably doesn't exist, like it's longer than the image size. And we hit this. Okay, it returns white apparently for any pixel that's beyond the image boundary, I guess. 255 all truths, 255 is all truths. No. Okay, I don't know if that would be a problem though, but let's see. So we assume it has 808 by 508 pixels. So we're going to do that iteration and work with that. So first we need, okay, for x equals 0, x less than 808, x plus plus Oh, I just realized, yeah, that my earlier calculation, the earlier value wasn't correct actually. I mean, we shouldn't have done 808 by 538. We should have done 807 by 537 because it always starts from its zero index. So I mean, it will probably still return white, but yeah, it's still white because it actually is white. But yeah, this should be the correct value. So yeah, so x plus plus. Then we're gonna have a second loop inside. And this is gonna be, I don't know how expensive this operation will be, but let's see. So we loop over the x and loop over the y. So get color of x and y, and take it to RGBA. Oh. So since we are calculating average, first we need to have all our colors. So we have an array of colors. We're not going to console the log because that's going to be a lot of work. And okay, maybe we don't need to convert to RGBA since we have the actual color value, which is an integer, or an integer that's the hexadecimal format. Okay, sorry, an integer that when you convert to hexadecimal is the same color. So we can just find the average of that integer actually without doing this conversion to RGBA. Find the average of R, of G, of B individually. We can actually just find the average of that. So let's give that a try. So we just push the color onto the array. Okay, and then what next? Let's take the average of that. Average color. Again, this is a first implementation anyway. We don't have to be entirely correct. But yeah, the average color that this give us is total number of colors. That's it. Number. Okay, so yeah, colors dots is yes. Is there some method in arrays in JavaScript? No. Colors dot reduce, and then this is the total. This is the sum. This is the next color, and return sum plus color, and you start out with 0. Well, okay, you really don't need this, but this will give us the sum of the colors, and then divide this by number of colors, number of pixels. That's okay. It's funny enough. It's funny that we're hard coding dimensions here. Let's have these dimensions we passed in from the command line. So we say width and height, and then width is going to be the third argument or fourth argument, whatever, and then height will be the next one. So yeah, file name, width and height. So we divide the sum of the colors by the width times height. Okay, and then we log that. Okay, let's see if this works. 808 538. Interesting. Okay, I'm missing something here. I am 100% sure I'm missing something here. Okay. Oh, okay. No, not necessary. Because the length of the colors should be, yeah. So we have this number, and then we can truncate it, like round it off, and then get a hex value from there. So let's keep going. I think What next? What next? We convert it to string base 16. Um, Average color. Yeah, I'm actually calling it average color in this case instead of dominant color because that is actually what we're doing. But once we're sure that this works for what we needed, then maybe we could call it dominant color. String base 16. And okay, sorry, we need to truncate it first because there's a decimal point. I mean, we could round it up depending, but I don't think it will matter much in the in the grand scheme of things. It's just going to be a subtle change in the color. But fine, let's round it off. Also, interestingly, it processed 808 by 538. That's 430 something million pixels in quite a short amount, like less than a second. So yeah, that's good to know. That's good to know. That's good to know that computers can do that. So this is the color in hexadecimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So okay, we are obviously some. Oh right, now I see the problem. Uh, this should have been in parentheses. This should have been in parentheses. So yeah. Oh Bakari says it's one. Okay, it's one indexed. Okay, I'm not entirely sure, and I don't know. But in this particular case, it doesn't matter anyway. I'll check the docs maybe to know how this library indexes the pixels, or if I don't know if you got that information from their docs or something. So we can know for sure if it's one index or zero index for the pixels. But either way, it doesn't matter much in this case too because the images are bounded by white, and if you access a non-existent pixel, you still get white in this case, which I think is a bad idea. It should throw an exception, but maybe it's a limitation of the library it's using or something. So anyway, let's go again. So yeah, earlier I forgot to put this in brackets, so it was actually doing divided by width and then multiplying that by height. So this is the value in hexadecimal, and we take that here, we get this color. Interesting. It's interesting. It's kind of a whitish color, but it's not white. So let's see if we can write that to an image and see how that would flow for us. Like if we converted that color, if we created an image that was just filled with that color, that dominant color. Creating new images. Oh, nice. There's an easy way to do this. So we can nice, this is a very nice library. So we can image with dominant color, GIMP. Okay, we can just use these dimensions, 256 pixels. Okay, fine. And then for a color, this is a hex value in JavaScript. Like this is an actual hexadecimal value, but I think passing the integer as well. Okay, yeah, passing the integer should work because this is just a number. But we made this into hex, so let's keep this separate. Color is 10. Sorry, what did I just do? Base 10. I shouldn't call it an integer. Actually, I should call it base 10 because that is what it is. So this is base 16. Or okay, let's just say hex. Color in hex. So what we want here is hex, and then we pass in the average color in base 10 here. Now, just okay, tracking back a bit for anyone that isn't maybe it's a bit lost on what happened here. The documentation here talks about how you can create an image and you set the pixel color of the image. Now this pixel color is, when you write a number like this in JavaScript, it takes it as being in base 16 format. Now remember that the base is kind of just a representation. The actual numbers are the same. So if I write a number like this, let a equals 0, and I write a number like this, let b equals let's say 0 0 and 0 0. This number is in hexadecimal format, but the two numbers are actually the same thing. So it's just different representations. So in this case, the number that this get pixel color returns is in base 10, and when we found the average, it was base 10. Convert it here, but here it's a string, not a number, like not a hex number. It's actually a string. So we're not going to use this. We can just pass in the number directly here. So if you pass the number as hex or as base 10, it doesn't matter. It's all the same to JavaScript. So yeah, average color base 10. So we are creating the color. This image is suffix by suffix. Okay, so what we need to do now is, I think we can do this without callbacks. Is this, I mean, this one, okay, fine, let's just use the callback. Even though I really hate working with callbacks then. So image the dominant color, and then how do we write an image again? There was something in the docs about that. At the start of the whole thing there was, okay, right, so just write it to a path. Right, dominant. Okay, let's see. Okay, cool. It wrote the image. So okay, so this is the image we have. You know what, I'm going to bring this file into our project so we can look at them side by side and see if, oh, okay, no, I think I'll keep them separately. Yeah, so is this the dominant color? I don't think, yeah, I think this is fair. I mean, the white border is messing up the image, but it's fair. But okay, let's try a different image. I'm not going to go with that because it's quite big and there are too many pixels. There. So I'm just going to look for another image on my computer. Okay, let's try this. I think this is a bigger image. Well, yeah, let's go with this. So what's the file name here? And this is a JPG file, 1920 by 1080. So this thing does not copy. 1920 and 1080. Oh shit, I missed the extension. So it's a JPG file. Again, I missed the dot. Okay, this is the dominant color, and let's see what's that like. Did you write it? Okay, let me delete this to be on the safe side. Let's see, what value did we even get for the previous picture? Okay. Oh wow, interesting. We are getting the same color. Okay, is that expected? That's the value we got for the previous picture. Okay, so okay, different pictures, but okay, this is Slightly light. This is lighter, but this is darker. This is darker shade. But here is the picture. I'm not sure this is the picture. Okay, this does not look very similar. I think this because this is like it has the multiple pictures. But then, okay, here's another thing I'm thinking of now. This gives us the average color in the picture. Like it's just a dumb mathematical calculation with it. And but personally, if I were for the dominant color, I think I would prefer to look at which color appears the most. So okay, another way we could do is look at which color appears most. So we track every single color that occurs, and at the end of the day, we pick the one that has the highest occurrences. But that, I think that may be a bit more expensive to calculate. But something like this now. So we track all the colors. No, this will be colors dot push. Now this will be become a hash. So essentially, we have. Let me clean the board. So yeah, and this is an example of how sometimes solving problems doesn't go the way you imagine. But you need to start from somewhere. When you start from a simple place, you can come up with more complicated solutions. Why is this coming back? I've cleaned the board. I don't just keep coming back. Okay. So we would have a list of colors, a map of colors. So we say this color, let's say red, appears 23 times, green appears 30 times, yellow appears this times, purple appears 5 times, and so on and so forth. But of course, the colors will not be red, green, yellow, and purple, but more like the actual numeric values of the colors or the hex values, but the RGB, the complete RGB value, like this. But I don't know. So, but the disadvantage of this method is that you are going to use a lot of space, because if you're going to record every single color that occurs in this image, okay, for these pixels here, they could probably be the same color, like they are the same color probably. But if you have a picture with lots of colors, you end up with nothing much. Like you end up with a very large list, and then we take the one that occurs the most. But let's give it a try and see if that'll give us better results. So we change colors to a map, and then we becomes colors get pixel color, so equals. So if there was something there, we add to it. If there was something there, we add to it. And if there was nothing, but then why am I doing this? So this is the color of the pixel, and so if there was something, if we already have a value for that color, we add to it. Okay, if there was a value for the color, add to it. If not, we mark it as 1. So then we would iterate over this list and find the one with the highest value. Okay, we can do that with a reduce as well. Sorry, reduce. Is that reduce? We have a list. I want to find the. No, reduce is a list operation. That would be iterating over all the keys and then checking. Okay, we could actually just make it objects.values or object.entries. So we iterate over all the. Okay, I'm gonna space it out, and then in this case we're not taking average anymore. We are taking the most frequent color. I mean, you could also probably just Google how to do this shit. like how to detect the dominant color from somewhere. And probably if I were to do this in real life, I probably would. But just for the fun of it, let's try and hack out what we can. Because this is a solved problem, right? It's not a complicated thing, probably. So yeah, for object or interest colors, give us the interest of the object as an array. So we're gonna start with, we're gonna reduce that. So it's gonna be an array like something like this. The key comes first, the value comes second. So you would have, let's say, okay, we don't even need object entries because it's really just the, okay, yeah, sorry, we need object entries. So you have the color, and you have the number of times it occurred, and then the next color and number of times it occurred, and so on and so forth. So yeah, we're going to work with that. So yeah, we're going to work with that object or entries. So the entry will be color and frequency. Right, this is how they do the structure and anything, right? And then the value we start with is 0, and the accumulator here is going to be the max, the one that the most frequent. So if you aren't familiar with reduce, yeah, we start out with, right, we are going to come back to this, but then okay, let's just do this at once. Return, okay, I'm gonna expand this. If so, we get the maximum. Yeah, you're right, we're moving the maximum, so we get the maximum of okay, does max work on an array? Oh god damn it, max actually works on an array, right? Thanks, Ivan. Yeah, max works on an array. But if we get that, it will just give us the value. It gives us the actual value, like the frequency, not the color. And it won't give us the key. So we need to do a search again for the colors with that key. And I'm not sure which one is better, frankly. If we use max on the values only and get the highest frequency, and then do a search again across the keys for the I think it's better to just go this way. So if the value, so if the frequency, okay, no, this needs to be an array, and so we start off with since the colors are numbers, we can still call it 0. Yeah, so most frequent color thus far is the color we've seen, is the color that has the highest frequency thus far, and highest frequency is the highest frequency. I thought I named this highest frequency thus far. Is the highest frequency we have thus far. This is what we set out to be 0, 0 initially. So if this value, the current value, has a higher frequency than the highest frequency we've seen thus far, then this is the new highest frequency. So we're going to return the array return now should have the name of the color, and then the frequency. Otherwise we just return what we are given. I think we could even make this, we could probably make this more efficient by combining it with the actual iteration. As we're iterating on the pixels, we can find the maximum right there as we are doing it. But yeah, let's just go with this and see how it goes. So I think this is correct. Yeah, we could use .find to find the key, but I'm not sure if that is better. Like let's go. Right. Math or max doesn't work on an array. It has to be spread, and that's one of the things that annoyed me about math or max out in JavaScript. And I go like, why would you not be able to work on an array? Before we could use spread, like when you are writing environments that don't work with spread, it was an annoyance to have to work with math or max. Like, I mean, please work on an array. Obviously, we will want to find the max on in an array. So yeah, okay, let's go. I think, well, if it crashes, then it crashes. Oh, get pixel color is not defined. What did we mean? Okay, right. This should be on footer. Okay, it's gonna take a while. Let's see. Can't read property apply of undefined. Oh boy. Oh boy. And there was a nan. Okay, you returned nan. Okay, that means we're missing something. We're missing something. Oh right. This returns an array, and I'm actually using it as this. So I should destructure this. I think I can leave this empty because I don't need it. White. Okay, screw white. Okay, you know what? Apart from white, no, this can't even be correct though because this picture, this picture, I don't think white. Well, let's we had a check that will filter out white, but then I think we're missing something in here. That I think we're missing something. What did I? Okay, I think we're missing something. I don't think this white returns is correct. It's a correct result of the computation at all. It starts out with 0 0, so it feels like okay. I didn't even really need this 0 0 actually. It could actually just start with the first color. The first color is the most frequent and it has the highest frequency. Okay, let's just take a look at what's inside our colors array. Entries, colors. It's going to be a large array, so I'm going to slice it. Start at 0, end at 20. Let's take a look at what is in here. Okay. Okay, these are the colors. 551. One. So most colors actually appear only once, and that was the problem. That was the problem with this method. Why do most colors appear once though? I think okay, it's probably the transparency that the transparency is different, but it's probably like the same shade of color. I mean, because all of these are the same. I'd say the same shade of blue, but maybe with different values of alpha. So I don't know. What do you guys think? And it's also interesting how these colors are very low values. Like compared to, let me slice the other colors. Let me move further down. What? Okay. Okay, so I sliced from 10 and to 20, but does that mean there's only like 30 colors in this thing? 30 pixels, because it's not just 30 colors, all of them have a frequency of 1. Okay, so I'm guessing there might be a bug somewhere here. Let's see. Colors, color. Oh, If there's anything in color, we increment it. Oh fuck. I have been beaten by post and plus increment again. This should be plus plus. So if if you have the plus plus after this, whatever you do, it makes no difference because it's going to return the initial value. But if you have the plus plus before, it returns the first value. So yeah, now you can see frequencies. You guys can see, right? So we have colors with different frequencies. So let's go again. What's the final? Okay, the final answer is still FFFFF. Okay, fuck that. Let's add a check that removes F. Okay, actually, just to verify that this is actually F, that the value is actually F. Let's do something. And okay, I think you guys are right. Yeah, I think you guys. Yeah. Okay. You know what? Let me go with the approach someone suggested. Oh no, never mind. I think I'll stick with this. I'll stick with this because I think that might make it slower if you have to like iterate over the array twice, because considering you have, if we go to the approach of doing an math.max, you could end up iterating over the whole array once, and then you do object.find and you iterate over the whole array again, like worst case scenario, which is still on, but will just make it will take more time. So I may change to that though, but for now, what I want to just right now is verify verify that there's actually white here and that it's actually the most frequent color here. So we want to get, no, I don't even need object or entries. I don't need this. Let's see if there's a white here. 0. So like 0 should be the value for white according to this. Okay, they are all strings, I think. I don't know. Okay, no, it doesn't matter. I think JavaScript, whether keys are always strings anyway, so it doesn't matter whether I write 0 or 0 in a string. But yeah, I want to see like the frequency, whether this is undefined or this is okay. This is undefined. Can you beat that? Okay, I'm gonna do a little. Color 0. I don't know if the white will be represented as 0 or 000 or something. I don't know, but I think it should be 0 since the rest of the numbers just look like regular numbers. Well, okay, let's try converting these to. Okay, I shouldn't be rounding anymore, by the way. Let's try doing the base 16 conversion. Oh fuck! Am I? Okay. I thought I was logging a different value. Okay, so let's try doing this conversion here. Yeah, let's try converting it to base 16 here. And in that case, I think I may be a bit more involved. Well, oh wow, now this one works. So I think there was possibly works. We're not sure anyway. But let's look at the frequency of white. FF. 1. Okay, so maybe there's one white pixel on the image. I don't know. But let's take a look at the dominant color that was returned. That's this. And our image, here it is. Okay, I think this is, I don't know, I think this might be better. I think this is a better fit than the average value we got instead. Now, of course, if I were building an app, I'll probably even want to go better and just take the colors at the edges. Maybe like if there are dominant colors at the edges, I could just take all the edges, because the idea is you want to make the person's profile flow from this image. So if you go with the colors at the edges, like in your calculation, you take a rectangle that you take, like this top rectangle here and this bottom rectangle, and you go with that. You could then, I think that might give you a better value for what you want to do. But yeah, I don't know. I think this is better. Let's try this with our previous image. Hmm? This is the color return for the other image. That's for this image. Hmm. Does it look good? Does it look like they might match? Well, I think this shade of green kind of looks a little brighter to me than the green that's here, but I think it's definitely green. I think green is definitely the more dominant color here. So yeah, there's that. So as to why that didn't work earlier, um why earlier it was returning white, I think I think sorry. So I think there was a bug somewhere, I'm suspecting, because mhm, I don't know how I don't know the internals of how the package represents the color white by default. I think it's 0, because 0, yeah, because most of the time it represents numbers as just a raw number. But I don't know. So my guess is maybe somewhere something happened with undefined or 0 as a string and number. It's probably a type issue from JavaScript, and so that's why we just kept on getting 0, which became FFFFF. Uh, so yeah, let's try on one more image. Let me find another image. Let me find an image from my desktop. No, I don't want you guys to see that. But okay, let's try this one. So I need to paste this. Okay. There's it's a JPG file, and dimensions 20 by 1218. Okay, let's take a look. Black. Well, a shade of black anyway. And I guess that's not bad. So yeah, I think, I mean, yeah, it kind of actually is. One more picture. Let me find one more picture. Okay, this should return a shade of blue, so let's see. And 1000 by 666. Where are the conspiracy theorists? Is this the same? Has this run? That is weird. It kind of looks like the same color I returned for. Looks exactly. Is it just me or that it looks exactly the same as the one you returned for the earlier picture? And yeah, it is a different file name. Would black be the dominant picture here? I don't know. I feel like it's going to be a shade of blue. And even though they have different hex values, I mean, it's obviously different hex values. It's obviously different hex values, but let me get that again. It's obviously different hex values, but they kind of look like the same. So I think they are shades of black. Maybe you know what? Okay, just so for things to be clear for us human beings, we're gonna log this to. This is a hex string, so we need to convert it to a base 10 number and then to RGBA. Into RGBA. Okay, this takes an int. So okay, how do we convert the hex string to integer? We could, I don't know if to string will work for that. Let's try. Let's see. Int to hex, into RGBA dot to string. I mean, it's 10. I doubt this will work. I don't actually think this will work because let's see anyway. I don't think it will give us the value we're looking for. Yep, I must be a number. So this only works if it's a number. Quickest way of converting a hex string. Hex string to base 10 number. I feel like this is the point where, okay, let me send it this. This might be the point where you need to, yeah, exactly, string. Okay, that's fair. Right, parsent also takes a radix. Let me see, is this the correct usage in this case? Why is it cast into a number? Parsent actually takes a string, so why is it cast into a number? Oh, I see what he's doing. So this, by passing this, we already have a number, so we might even already have what we need by passing this to the number constructor. Let's give this a try quickly. If we do number 0xdc, yep, we have to turn into the number that we need. So all we need here actually is number and 0x plus that, yeah. Let's see number 0x. Okay, so RGBA, yeah, 13767. So yeah, it is more of blue. It's more of blue, less of red and green, but kind of dark. Not sure why exactly it's so dark, or if this is what it's meant to be even. Okay, let's also log the hex value. So just to be sure that my ID isn't maybe caching something. Okay, it's a dark blue eye apparently. What? What the fuck? What just happened to my? Oh, why is it 1, 2, 3, 4, 5, 6, 7? Why is it a 7? Why is it 7 digits? God damn it. Okay, let's try with the other picture. Okay, not digits actually, because hexadecimal wouldn't be called digits. I think digits is only for decimals. That's what you call them. Okay, I'm not sure exactly why it's 7, but I think we can normalize it. X. Not sure why it's 7 all of a sudden, because it returns 8. This returns. Just gonna do a quick color. This logs 8. Yeah, so these are 8. Okay, sorry, not more than 8 anyway, but these are all, those are 8 integers. So let me see what happens when you convert it to a hex string. Okay, that was probably not a good idea. Probably not a good idea. Oh, colors. How do I get a random? Ah, shit. Okay. Oh, never mind. Okay, I think. Okay, let's try one picture, and then I think we'll call it a day for now. The aim isn't perfection, but the aim is to get there anyway. And then also, I want to try something as well. What happens if we specify a rectangle for this? Like, you know, here we're specifying the full length 1 by 666 of this image. What happens if we decide only to specify part of it? So, you know, it's only the pixels that we specify here that the code is going to iterate over. So if instead this is 1000, 666. So instead, what if we decide to go with let's say the top image, so 1000 by 400. No, it's 400 is more than half, so let's 1000 by 200. Let's see the dominant color returned. Okay, I'm pretty sure there's something wrong here, because how can okay, I think I should delete this. Or am I even sure the code is updating this? Okay, I have no idea what's going on. Why is this meant to be black? I think that's just black, not white something. Okay, let me do a test. What if I change the pixel color to 0? Oh fuck. It's just writing a black image. Ah, god damn it. What happened? God damn, what happened to my ID? I mean, it was working before. It was writing the right colors before. And then all of a sudden now everything is black. Let me try a restart. I don't know if it's the ID or it's the library or if there's a bug in code. Starting that. But let me try. Is there any service I can put in a color? Okay. Okay, I think I can. I just need a color wheel. Yeah, a color wheel should be fine. I just need to be able to enter this color and see what happens. Yeah, come on, this time hasn't started. Okay, so yeah, cool. Oh, for fuck's sake, I think something is wrong. Something has gone wrong with And PHP some isn't starting again. Well, it doesn't matter. Oh, now it's starting. Either way, let me just open my terminal. Not sure what is going on here today. Okay. Oh no, this one will because I'm here. Now I'm here. Still black. Fuck that shit now. So we take this color, take it to the color wheel. Yeah, and we enter the color. So it's a blue, it's a shade of blue, light blue, like a quite light blue. But then remember, we only constrain it to the top rectangle. Let's see what happens when we go back to using the whole image. So this is the color we have, and this is kind of reddish. No, this is not the full color. This has 7 figures. There's an extra F. I don't know why this isn't. I don't know why this color calculator is not. I'm pasting the entire color, but it's not letting me. Okay, it only accepts six figure colors, right? I think if we pad it with a 0 at the start, we should be fine. We should be fine. So 0. Okay, so it's a bluish color. Yeah, but it's quite light. Then for the previous picture, that was the other one. For this one, we get this, and the dominant color here is this 0 and this. That can be right. 1 2 3 4 5 6 7. Alicia Cara, 1922 or 16. Green, interesting. Okay. I'm not entirely sure what this is up to. Wait, this isn't. I'm sorry. Hold on. Okay, this isn't the same thing. This is 600 FF, and what is here is 600. Okay. Okay, transparency, and doesn't allow it to specify. Okay, I don't like this. I don't like. God damn. Okay, let me just open this. Let me see if I can open this file normally. It could be that it's not overwriting the file for the dominant.jpg. And let me open this. Okay, it actually is just writing a black pixel. So maybe does this take parameters? Oh shit, I forgot I set this back to 0. Okay. Still, sorry. Still black. Still all black. Okay, I'm not entirely sure what's going on here. Why it's just writing all black to it. Oh. Okay, this is starting to get quite annoying. Okay, no idea what is going on. No idea what's going on here. Try to clear this. Delete and recreate it. Okay, still black. All right, I think we'll just stop it here because it's been quite right. But it has been quite fun anyway to see what's going on over here. Oh, I see. Interesting. This is black. Okay, this should be black for Alice for the first one. For the second one, this should not be black or as black as that. Yeah, so this is the actual color. Yeah, this is the actual color, blue. I don't know why this is failing. It's not writing any longer. So maybe there's an error and actually we haven't been handling it. Or I don't know. Well, yeah, I don't know why this is not writing. Should I try PNG? But this is the actual color that was returned, which is blue as we expected, and that's quite nice. No, PNG still not working. So I think maybe I should take some time and come up with a better representation, like a better way of representing the dominant color, like maybe type it to a web page or something. I don't know. Let's try with the final example we used earlier. Okay, this one. That's the airplane picture, and the color is this, which nope. Okay, it works now. I think I don't know. Oh, okay. I think. Okay, I think 5, 6, 7, 8. I think I have an idea of what's going on. Okay, it has to do with the transparency. When we have the 8, not transparency, but like the full range. When we have the 8 digits, 8 figure 1 hex values, it works. But when there are 7 figures, it doesn't work. So let's see. 0x. No, this is where we get it from. So this is the color. This is the color, most frequent color in base 10. Okay, it's actually no longer in base 10 right now. It's in base 16. Since we are converting to string here, 16. Let's see if we try pad start. We want to pad it with 0 to how many? Oh, sorry, max length comes first. Are you serious? Okay, max length is 8. So if we go back to the previous picture, yeah, we have it starting with 8 now, and then yep, this is the blue that we should get for the Nicki Minaj photo. Nice. So yeah, this works. Let's try another photo, a different photo entirely, since this has been so stressful. Lastly, goddamn, software development will embarrass you. JavaScript will embarrass you. Okay, so wallpapers. Okay, this is going to be interesting. So let's try this one. File information. No, shit, I mistakenly cleared that. Oh, what the fuck, did I hit enter? fuck? Okay, and then 1024 by 625, 1024, 625. Okay, so this is the color black. Yeah, that's black. And yes, yeah, black occurs the most here. So I think we've got it working. We've got good pictures now, and we've been able to see how this can get the dominant picture, dominant color in the picture. Okay, I want one more. Let me try one of my favorite pictures, I guess. So, 1920 and 1080. Yeah. And here is the color. Nice. So we put it side by side, and you can see that it actually makes a nice, it actually does make a nice background from this. So that's nice. Yeah, we got the color that appeared here the most. So thanks guys, thanks. It's been quite a ride, almost 2 hours, 2 hours pretty much, and this was fun. Also frustrating. Probably if I had been a bit more careful and paid more attention, I guess we would have had less frustrations. But then I think we've all probably learned something, maybe most of us. All right, so thanks guys, and bye.